we are going to see what happens if we stick in just I times theta into this. So notice that if we put in the sum k equals 0 to infinity of I times theta to the k over k factorial, we can break this into this sum over the odd or the even. The sum k equals 0, infinity I theta 2k plus 1 over 2k plus 1 factorial, like this, and then the sum over the even, say m is equal to 1 to infinity I theta to the 2m over 2m factorial. And then what happens to this thing? So this is sum from k equals 0 to infinity. Let's pull out this I to the 2k plus 1, right? So what is I to the 2k plus 1? Let's put it over here. So I to the power 2k plus 1 is equal to I, and then I to the 2 power k, which is equal to I times minus 1 to the k. Yeah? So what we have here is going to be minus 1 to the k, put out the I all the way here, and then we're going to have just theta to the 2k plus 1 over 2k plus 1 factorial. Okay, and then from this thing, what happens? We're just going to have sum m equals 1 to infinity, and we're going to have minus 1 to the m, theta to the 2m over 2m factorial, like this. Yeah? And as you guys know, or as you people know, this thing is just going to be cosine of theta. And this thing here is just I sine of theta. So this is what we're going to motivate for the following thing. So we can define the exponential function e to the z, which is e to the x plus iy, in the following way, to be just e to the x. So this is the definition. E to the x, we know what it is. It's the exponential function. E to the I theta, we know what it is. It's defined. Okay. I should perhaps say. Should perhaps write it like this. Write it like this. Cosine of y plus I sine of y. Yeah. So if we define it like this, then what we know? Then the above calculation is that we have this is given by this power series equals 0 to infinity I theta to the k over k factorial. Yeah. And if we just do this, e to the theta itself, or just e to the x, e to the x itself, then just from this thing, there's no imaginary part. This is just e to the x. Which is also just given by the power series, the sum k equals 0 to infinity x to the k over k factorial, as we know from just calculus, right? So what we see is that if we define it this way, then it actually agrees with the power series on the imaginary axis and on the real axis. And later we're going to see that if we define it this way, actually this power series actually represents e to the z everywhere. You know? But that we'll have to see later. What you can check pretty easily is that if you define this function like this, and this is perfectly well-defined function from the complex numbers to the complex numbers, then this thing satisfies the Cauchy-Riemann equations. Just check it, just do that calculation. However, that doesn't, based on what I've shown you, that doesn't imply that it's holomorphic yet, because what I've shown is that if it's holomorphic, then it satisfies the Cauchy-Riemann. The reverse implication is also true, but that is harder. That can be done with the hypothesis that the function has got continuous derivative fairly easily, but in more generality, it's actually harder, perhaps quite a bit harder. So this thing, okay, is nevertheless. So we're gonna assume this thing, which we can't prove yet, is true. This thing actually is given by this thing. It is given by this power series. So this guy is an example of a holomorphic function, and we're going to try and understand what it does, and it does surprisingly dramatic things. So see if I can squeeze this in. Maybe I can squeeze this in here. So let's take a look at its behavior. Let's look at the complex plane here, and let's map it over here with the complex plane. Okay. Let's see what this function does. If we take a strip from pi to minus pi, and we map it with this guy, e to the z, let's see what it does. Well, if we take a line like this, so let's fix some x0, and let's take a line like this which goes through this strip, okay? So then we are varying the y from minus pi to pi, but remaining the x fixed, right? And then let's look at this definition. So if we do that, then the y is changing. Yeah, the y is changing, yeah, it's going from minus pi to pi, but the x is remaining fixed, right? So this thing, as we move along this strip right here, x0 is fixed, it's this thing, and this thing is just the unit vector in the complex plane rotating around from minus pi, which is over here, all the way to pi, right? That's all that we're doing. So we are going to get a circle whose radius will be like this, e to the x0, yeah? Because we will start right here, minus pi, and we go round and round and round like this. That's what it does. And if we do the same thing for some x0 over here, and we get a much smaller circle, and if we do the same thing over here, we get a much bigger circle. So these vertical lines are mapping onto circles, yeah? If we take a horizontal line like this, so now the y is fixed, so it's y0, and we're going to have the x will be changing, yeah? Then what happens? So y is fixed, so then this is defining the angle, okay? So this is the complex number part, or this is a complex number, and this is just a real number, right? Yeah? So as x varies, as x goes towards minus infinity, we go towards 0, right? We have e to the minus x for a very, very negative x. We go towards 0. And as x gets positive towards infinity, we go towards infinity. So then this blue line here is actually going to form this ray going out like this. So where this is where we go towards minus infinity, and this is where we go towards positive infinity. And then this thing here is going to be given by angle y0. Yeah? And note in particular that at the crossing point of these lines, this point right here, sure enough, they are crossing at at 90 degrees. The angle is being preserved, which is what we know has to happen for holomorphic mapping. And what this little calculation also shows is that we are mapping this entire strip onto the complex numbers except 0, right? So we're mapping the entire strip onto the complex numbers except 0. Well, let's put that here. So E of z sends this strip, which I'm going to denote like this, so the real numbers cross product with, let's do it like this, I times minus pi. Pi, this thing is sent to the entire complex numbers, take away 0. No? Cool. But from this definition right here, if we consider the strip which we just get from moving up a little bit from pi to 3 pi, okay, then the same thing's going to happen, right? Because this expression here is periodic in pi, right? So whatever's happening here, if we move up by 2 pi from here, exactly the same thing's happening, right? So it's going to map this strip to the same thing, right? So we can cut up the entire complex plane into these horizontal strips of width 2 pi, and every single one of them is wrapped around the complex plane, right, in the image. You know? So this is a really crazy behavior. This is much more strange and complicated than z to any power k, which we can sort of visualize just by making a slit and then wrapping something around. This is taking the entire infinite horizontal strip and wrapping around the complex plane, and it's doing this in a holomorphic way, and it's doing this in a way which is differentiable at every single point. And later we'll see it's even more than differentiable. It's differentiable to any order. In fact, it has a Taylor series. It's analytic. Yeah. So very dramatic, strange behavior for a function that locally preserves angles everywhere and is differentiable everywhere. It's quite a surprise that such a thing exists, but it does, and it's not. These things are not particularly hard to work out. So we have this particular example of a strange complex, of an unusual, surprising holomorphic function. And note it also recovers the ordinary exponential function that we know, because if we just look on the real line, then on the real line, then this is the exponential function that we know, right? If y is just 0, it's just the ordinary exponential function. So this monster contains the guy that we know well from calculus, and it just contains it when we restrict what happens to the real numbers. It sends the real numbers to the real numbers. Yeah? So part of the familiar old exponential function we've known about for a long time is inside this guy. All right, we're going to talk about log functions and trig functions when I erase this board. Okay, so let's discuss more this strange function, what it does. So we've seen that it takes all these horizontal strips like this. So it's minus pi, 3 pi, and so on. And it maps them, wraps them all around the complex numbers, except 0. Yeah? So in particular, so this is z goes to e to the z. If we take some complex number here, say w, and we ask ourselves what gets mapped onto w, well, as we've seen, for any one of these strips, for sure it maps around the entire complex plane except 0. So in each one of these strips, we're going to hit this at least. In fact, we're going to hit exactly one time. It's kind of clear from our construction. In each one of the strips, there will be one guy that hits this, right? And because whatever's happening in the strip is happening on every strip moved 2 pi up, 2 pi down, for any multiple of 2 pi actually, then the same thing is going to happen here, and then here, and then here. So all of these blue dots, we mapped all onto W. So the inverse of e to the z is no longer going to be a one-to-one function, which it is on the real line when we do calculus. E to the x is a monotone function, satisfies the horizontal line test. It's invertible. We have the inverse is called natural log. No such thing happening here, right? But the inverse seems to have quite a regular structure. In fact, if we restrict down to some particular interval from minus pi to pi, then it will be invertible, right? Because there's only one copy happening there. So recall some notation. So given z inside the complex plane, then we can write z as mod z and then e to the I of theta for some theta, right? And theta is not unique because every multiple of 2 pi is also going to do this representation. But we can choose what we call the principal argument, which we're going to write like this. So arg of z is the one particular number which, like this, or it might be the way around, which satisfies this, which is inside this interval. There's only one guy which will satisfy this, so that z is equal to mod z e to the I arg of z, right? That's the one representation of the angle inside this particular interval. And this thing we're going to define to be equal to arg of z plus 2 pi k for all k which are integers. So this thing is actually an entire infinite set of complex numbers. Sorry, this is an entire infinite set of numbers, of angles, right? So this is at least notation in Zill's complex analysis book, I guess somewhat standard notation. So let's try and understand what the inverse of e to the z will be, given that we have a fairly good picture of the way it behaves. So if we restrict to just minus pi to pi, then what happens? So if, let's call it, give it a name, let's call it log of z is the inverse of e to the z restricted to this strip here, minus pi. Let's do the r first. Then what properties will it have? Then it has to have this property that e, let's write like this, z has to be itself again, right? But then this thing is just given by e times the real part of this guy plus I times the imaginary part of this guy, which by definition of e, how we've defined it, is this thing, e of the real part of log of z, and then times e to the I, the imaginary part of log of z. So if we just take the absolute value, this thing is just a complex number of length 1, right? So taking the absolute value, we have that mod z is equal to just e times the real part of log of z. And therefore, if we take natural log now, I mean real natural log from the real numbers to real numbers, which we'll denote by log to the base e. So let's put over here, log to the base e is this natural log from real numbers to real numbers. If we do that, then what happens? Then we have that log to the base e, again, this is notation from Zill, is equal to this real part of log of z. So we understand what the real part of this function has to be, right? just by taking absolute values. And now if we look at the direction of these complex numbers, right, in this guy, then the direction is denoted by this thing, right? So we also have that z is equal to mod z e to the I times arg of z, which is equal to this thing, right? So let me put this since. So from the line above, let's call this thing star. From a star, we have what? We have that imaginary part of z has to be equal to this thing plus any 2 pi k, right? Because actually, just write it out in steps. So we have from star and the fact we've just found out that mod z has to be this thing, we have that e to the I times the imaginary part of this thing has to be equal to e to the I arg z. Yeah? And the only way that's true, we could also write e to the little I arg of z. This implies that imaginary part of log of z is equal to arg of z plus 2 pi k. Let's write it like this, i.e. that's the same as little arg of z. Yeah? So, what that means we've completely defined what log of z has to be, right? Because its real part over here is given by this. So it's log the base e of mod z. That's what it does to the real part, right? And the imaginary part we've got from over there is this, which, as we know, is like this infinite set of real numbers, right? Arg of z is this infinite set of real numbers. Did I erase it already? No, here it is, right? Yeah, and let's compare it to a picture. Well, if we restrict this thing just to minus pi over pi, then it is indeed a well-defined function, and we would have this thing. For e to the z restricted to just one of these strips. Yeah? Because in this case, if we were restricting z to one of the strips, so the inverse is going directly back to the strip, then it is not arg plus anything else, it's just capital Arg by itself, which is by definition just in this strip. Yeah? So the restricted mapping from here to the entire complex numbers minus 0 is invertible by this guy. Yeah? And the more general inverse is not a traditional function. It's not a one-to-one or many-to-one function. It's a one-to-many function. It's a set-valued function. The general inverse is given by this. So better perhaps to have different notations for these two guys. Maybe I don't know. I will say log n and then put a tilde or something. log E, C, and now we have this. So it's every Z over here, we have an entire infinite set. This is defining an infinite set, right? And that infinite set has its real, it's every number inside that infinite set has its real part is given by this, but the imaginary part changes, and it's exactly this picture here. It's exactly all of these dots right here, right? Because each guy is just moved up or down 2 pi I from the other, yeah? So we recover in the language of maths what our picture tells us. Our picture tells us that that's what happens. If we consider all the images, all the Z that map onto W, we get a thing like this, and then the language of math confirms it. That's actually what we get. So that is the log, the general log function. And again, it's a more complicated type guy.